Okay, biological psychology. I want to go over a little bit some of the things, in fact, all of the things I talked about on Tuesday, and then we'll go on to the right hemisphere, and I want to tell you about something amazing that happens when you cut the fiber pathways linking the right and left hemisphere. As I said before, we have Broca's area producing the words, we have the melodic speech area producing the sounds. They interact in a rope of fibers, axons. Also in the temporal lobe, you have Wernicke's area, which is perceiving the sounds of language. And in the right temporal area, you have a brain area that's perceiving the emotional sounds of language. And these two areas of the brain are also interacting by a rope of fibers which cross over and connect the two halves of the brain. So the two halves can share different information so they can work together. But it turns out, as we will discuss in the later part of this class, if you cut those fibers, if you cut the fibers linking the right and left half of the brain, you're going to end up with two people in the same head. Two people with different memories, different goals, different desires, different tastes in food, different tastes in television programming. Yeah, I know this for a fact because I've seen these patients, I did research on them, I published on them. Yes?
Is that considered split personality disorder?
No, this is something so unique that you'll actually, the person left half of the body will try to do one thing and the right half will try to do something else. It's really like having two different people in the same brain, in the same body. Yes?
Did they ever get into a fight with themselves?
Yes. Yeah. Yeah, examined patients were actually started fighting, the two halves of the body started fighting. And hand actually tried to strangle him, and he had to stop it. Okay, we talked about the left hemisphere, the properties it has. Okay, so here we have our left hemisphere. And as we know, Broca's area damaged here, you get expressive aphasia. Damage in Wernicke's area, you get receptive aphasia. And I want to talk about a little bit today is how does information get up into the auditory area in the first place? And the kind of processing that occurs. So the sounds are processed in the inner ear, and then what happens is the sounds travel through the auditory nerve, and it goes to two different directions. And one direction it goes is to the brainstem. We have here, this whole thing's the brainstem, this is the midbrain, this is the pons, this is the medulla. If you look at a reptile does not have all this neocortex, but they do have a brainstem. If you look at a lizard, they don't have all this neocortex, but they have a brainstem. If you go to a fish, they do not have all these higher structures, but they have a brainstem. So brainstem, from an evolutionary perspective, is a very ancient structure, and it takes care of very basic processes like controlling breathing. So you don't have to think about it. Take a breath, let out, take a breath. You don't have to do that. No conscious need for breathing. It also regulates heart rate. So a lot of different capacities are regulated within the brainstem, which we'll talk about later. But go back to auditory information. So you hear these sounds, go in, make it to the inner ear, go through all this high processing. It's already being processed in the inner ear, and then it goes to two main different directions. And one direction it goes is to this structure right here, which is part of the midbrain. It's called the inferior colliculi. The auditory information goes to the inferior colliculi. And you see colliculi up there. Inferior just happens to mean the position. It's not like social status or anything or wealth. It just happens to be where it's located. The word colliculi, that comes from the Latin referring to culla. And if any of you speak Italian, you will know that what it's referring to is the buttocks. Okay, so what they're doing, whoever first looked at the structure, it has this little rounded protrusion, so it made them think of a buttock, so they called it a colliculi, a culla. And there's two of them there. Actually, there's four. Okay, here's another looking straight down, superior looking downward. The other one was a lateral view. So here we have these inferior colliculi. So you have all this auditory information going into the inferior colliculi, where very primitive type, more analysis is being taken place. At the same time, visual information. Visual information comes in through the optic nerve. Turn the brain upside down and look. Here you have your optic nerve, which would go up to the eyeballs, okay, to the retina. Visual information is coming in, is being highly analyzed already at the retina, within your eyes. Already a lot of processing is going on. That information, the visual information, also goes in two directions. And one major area it goes to is the colliculi. It goes to the superior colliculi. The superior. So here we have the inferior, which is processing auditory information, and here you have the superior colliculi processing visual information. Now this is actually a pretty good, cool arrangement, because what happens, you hear a sound, it could be a sound, a loud sound, and what happens is the two colliculi being right next to each other are sharing information, the visual information, auditory information. So you hear a sound, and you will turn and look. Your eyes will turn and look towards it if it's a loud enough sound. This is almost a reflex, doesn't require conscious thinking. So you hear the sound, your head turns, your eyes turn, because it's all being controlled by the brainstem. This is something that confuses a lot of people who have family members that go into coma, who have massive brain damage, and they're laying there. Because what will happen, somebody might walk in the room, is laying there, and the eyes will turn and look at them. They go, oh, they know I'm here. They're not really unconscious. They're really processing all this information, when in fact, all the brain from here could be gone. I mean, you just scoop it all out, and if you leave this much portion, as long as blood flow is still going, you're still going to get that, make the sound, the eyes turn, the head might turn, you go, oh, they're really conscious, they know I'm here. No. But that's why, if you pay attention to news, there's a Shiavo case, been in this unconscious state, coma for all shriveled up for like 10 years, and they want to finally pull the plug, and people go, oh, when I go in there, she looks, I talk to her, she'll turn her head. Well, that's just the brainstem. It's a reflex, and it's a cool system because then you don't have to go, I heard the sound, I think I'll turn my head. It's just, you just do it. Okay, so, two colliculi. There's actually four colliculi. Again, this is looking straight down. So it's like, okay, so you can see here's the two, and information from the right is going to the right colliculi, information from the left is going to the left colliculi. And we have a question.
You said there's four, but what about the facial colliculus?
Facial colliculus also has a rounded protrusion, but don't pay attention to that right now. Just ignore that part. We just want to be concerned with these colliculus. For this reason, because of similar names, they also call this part of the brain the tectum. That's just another word, so there's more than one word. So you can call it the colliculi, the little coulas, or you can call it the tectum. All right. So information from the auditory area, from the ears, as I said, goes to two different directions. This is the thalamus. Thalamus is located in the central center part of the brain, right above the hypothalamus. Hypo means below, hypothalamus, totally different structure. But the thalamus, all sensory information, except olfaction, except sense of smell, touch, hearing, visual information, before it gets to the neocortex. Before it gets to the neocortex, it first goes to the thalamus. Auditory information goes to the medial geniculate nucleus of the thalamus. Oh, there it is. It's actually hidden in here. The geniculate body, the lateral and the medial. So auditory information goes into to the thalamus before it makes it to the neocortex. And it's called the medial geniculate. Geniculate, they named it that because geniculate in Latin refers to the knee, a bent knee. Somebody thought it looked like a knee, so they called it a geniculate. So it's called the medial geniculate. So we have auditory information, two paths, one going to the brainstem, for all these reflexive actions. Another's going to the thalamus, where more processing is occurring. Right next to the medial geniculate is the lateral geniculate, and that's where visual information goes. So here we have in adjacent parts of the thalamus, the medial geniculate, the lateral geniculate, and there's more complex processing. Before it gets to the neocortex, where higher reasoning thought, what makes us distinctly human, before it gets there, it's already being processed in the thalamus. It's also being processed in the brainstem. And if I had the right picture, I could show you how the colliculi are right about here. And so they're almost adjacent. So these areas are right next to one another, and they can also communicate. So what I'm trying to say is all this incredible amount of processing is occurring within the brain before it ever makes it to consciousness, before you become aware of it from a conscious perspective. Visual information then goes to the occipital lobe. It goes to the primary visual cortex. Here's the primary visual cortex. So we see the information is making it to here, it gets to the lateral geniculate, and then it goes up and it makes it to the primary visual cortex. And as we discussed on Tuesday, if this area, area 17, the primary visual cortex, if this area and the surrounding association areas were destroyed, the person would be cortically blind at the cortical level. But the brainstem might still respond to some visual input, something a person might turn. What'd you see? Oh, I don't know. I didn't see anything. It's the brainstem. I'll go more detail on that later. So here we have all this visual information making it to the visual cortex. It's already been highly processed, and at the level of the visual cortex, what's happening is that area 17 is analyzing the visual, where it's located in space. Is it a circle? Is it a square? And then what happens, that information is transferred to areas 18 and 19, which is the visual association area. This is again looking at the left half. This is primary visual cortex. Here you have what's called association cortex, area 18 and 19, visual association area. What that means, primary visual area. If you went in with an electrode and stimulated, the person might say, I see color, I see a square, or I see a line. But what happens in this area is it associates the different visual percepts. So you can go, it's blue, and it's round, and it's floating in air. So it puts the different associations together to create simple visual concepts so you can recognize a tree as a tree. Then what happens is all this information is transmitted to the inferior parietal lobule, which we spoke about before. This is an area that's unique to primates. The angular gyrus is unique to humans. And what this area of the brain, the IPL, inferior parietal lobule, it assimilates associations. It assimilates. So it goes very simple, somewhat complex, highly complex. It assimilates and is also getting auditory information that's already been highly processed. It's getting tactual information that's already been highly processed. So we have this particular area of the brain which assimilates association, so you can put sound with vision, with touch, so you can visualize. If I said to you the big black dog, you'd be able to visualize dogs, big black ones, you can visualize them barking, you can think of different breeds, all the different names, and all of this is actually taking place in this one particular area of the brain. Now let's go back to the auditory. So the auditory information goes to the colliculi, and then it's also going to the geniculate, and then it's transmitted to the primary auditory receiving area. In the occipital lobe, we have primary visual receiving area. In the temporal lobe, we have a primary auditory receiving area. In the parietal lobe, we have a primary receiving area for touch. Then we have an association area in each of these for vision, for touch, for audition. So what happens, the auditory is going to the inferior colliculus, and it's going to the medial geniculate. Visual information is going to the superior colliculus, and it's going to the lateral geniculum. Auditory information from the medial geniculate then goes to the primary auditory receiving area. You have a primary auditory receiving area in the left half of the brain and a primary auditory receiving area in the right half of the brain. So it's at this level it finally makes it to the neocortex, where sounds are heard, where you can say, I hear something. Goes through a lot more processing, and then it's transferred to the auditory association area, which in the left hemisphere is Wernicke's area. And here more complex associations are formed. Now, in my years of experience, I've seen thousands and thousands of patients. So basically everything I'm telling you I've seen in one place or another. I'll tell you a little bit more about my background at another point. But sticking right here to right now, it's primary auditory area. If a person were to have bilateral strokes, bilateral damage, bilateral meaning on both sides, and destroyed the auditory receiving area on the left and on the right, the person would become cortically deaf. I'd be talking and you would not hear anything. Explosions could be going off, and cortically you would not be hearing anything. You would be cortically deaf. Still, if there was a sound, you might turn your head. Doctors who are not up on neuroanatomy, people could be described as faking because don't realize there's other areas of the brain that could subserve the same capacity. But you can be completely deaf with bilateral destruction. If instead the destruction was right here, just into the left primary auditory receiving area, you would become word deaf. You'd hear sounds, you'd hear somebody knocking, you might hear somebody singing, you could hear birds tweeting, but you wouldn't be able to hear me talking to you. You would not hear it. You would become cortically deaf. You would be deaf for words, not cortically deaf, excuse me, that's bilateral. So you become deaf for words. It's called pure word deafness. It's an actual medical term, pure word deafness. And you would know you were deaf for words because the rest of the brain that's perceiving auditory information would realize it's not getting these sounds. Now, thinking instead, it's an older person, little stroke, and you can have little tiny ones. A little piece of globule gets stuck in the little blood vessel, and you just have a little blowout area here. And what's happening, the person now is having trouble. You're having a conversation. Can you repeat that? I didn't understand what you said. I'm having hearing problems. You go to the doctor, get all these ear implants. There's nothing wrong with the ears. The person's actually having little strokes, which is making it difficult for them to process the sounds of language. Okay? So that can happen in real life, and it could happen to some of you as you grow much older. Raising a question or pointing at the ceiling?
If they can't understand the word, but they previously knew it, if they say it, will they not understand it?
If they talk, they won't hear it. They'll hear sounds, but they won't be able to hear, it'll just,
Even though they're
like
saying
that. It'd just be a
sounds.
noise, a sound without.
Okay.
If instead the destruction was in the right temporal area, in the right primary auditory receiving area, if you had this kind of damage and you're at home and somebody knocked on the door, you wouldn't hear it. If the phone was ringing, you wouldn't hear it. If you were outside, you wouldn't hear the wind, you wouldn't hear birds, you wouldn't hear water. Somebody would come to you and go, they've been knocking at the door for 5 minutes. Why didn't you? Oh, I didn't hear it. And they go to the door. They can still hear language, but it's environmental, musical sounds. They would lose that ability to perceive, and also to perceive emotion. Because it's emotional and melodic. You wouldn't hear music. You wouldn't hear emotion. So he says, I love you. You wouldn't hear your I love you. So this is what the right auditory area is doing. There's actually a rope of fibers going all the way to Broca's area. Rope of fibers connecting all this vicinity, all this area. So you have this tremendous amount of wiring going on. So we know that when you perceive, you hear the word, hear the sounds, it goes to Wernicke's area. If I said to you the big black dog, you know, do you own a big black dog? The information would go to the inferior parietal lobule, which would analyze the big black dog. It's big, it's black, it's a dog. What's it look like? Do I have one? Would put all this information together, and then it would transmit via this rope of fibers called the, well, this is called the longitudinal fasciculus, and it's also called the arcuate fasciculus. And yes, I will ask you questions about that, maybe. So we have this rope of fibers, and I'm asking the question, do you have a big black dog? If I was to destroy Wernicke's area, you would hear blip blip dog, blip blip dog, dog blip blip blip. You would have no idea what I'm saying. Because Wernicke's area is separating all those sounds, putting them in their temporal order. It goes to the parietal lobe. If it's normal, it goes to the parietal lobe. If the parietal lobe was damaged, you might have word finding difficulty. But we're not going to talk about that. So, do you have a big black dog? Goes to Broca's area, and you say no or yes, I do not have a big black dog. Now, how does that work? It works like this. Here's your frontal lobe. Here's your primary motor area. Broca's area is like an association area. What Broca's area is doing, it's immediately adjacent to this area. What's next to it? Well, here's the tongue, the lips, the mouth, the face. What Broca's area does, it actually programs, like a little computer punching in the code into the motor area, so you move your mouth, your tongue, your lips, so you can say the words. So it's a pretty neat little system. So Broca's area receives all this auditory, and then it projects it to the motor area, and the person can say, yes, I have a big black dog, or no, I do not have a big black dog. And what else they might do while they're talking is they might be waving their hand around going, no, I don't have a big black dog. Why might they be waving their hand around when they're doing all this? It's because all this area, you're transmitting Broca's information to the motor area, you actually get spreading excitation. Spreading excitation, which actually will activate surrounding tissues. Okay? So a person might be talking and they're waving their hand, but the hand use is also related to language. For example, if I said to you, I want you to write for me, I do not have a big black dog. It's Broca's area which sends that information to the hand so that you can write it out. So if you had damage to this part of the motor area, well, let's go back. Because all these areas are linked, if a person has Broca's aphasia, expressive aphasia, they're going to be paralyzed. Half their face is going to droop on the right side. The mouth will be drooling a little bit, their face will be weak, and they'll be paralyzed. So there's no mistaking Broca's aphasia or massive damage. And that's because this whole area will be destroyed. So a person can be paralyzed as well. Paralysis. And it can be to varying degrees. Again, I keep giving the most extreme examples. Let's go back to our temporal lobe. The left temporal lobe is processing lots of auditory information, and it turns out that in this part of the temporal lobe, it's storing auditory verbal memories. My name, Dr. Joseph, is being stored in your left temporal lobe. The name of the street you live on is stored here. Sentences, things you read in the book, conversations you're having. All auditory, linguistic, verbal type information is being stored in the left temporal lobe, and there's two structures in here involved in memory. One of them is called the amygdala. We've talked before about that. Emotional memory. Another structure called the hippocampus, which also involved in memory. We'll talk about that more next week. But in consequence, if you had damage in this area, you would have severe problems with verbal memory. I could say to you, give you your assignment, you could read things, in a few minutes you start forgetting all that information. Okay, so the temporal lobe is storing all this auditory information. Visual cortex. Primary area, simple percepts, association area, more complex percepts. But it turns out if you start going into this area, extremely complex percepts, including, for example, faces. Here they might have neurons that recognize a certain spot. Over here, ones that respond to circles. Over here, ones that respond to squares. But you get down into this area, you have neurons that respond to specific features. There might be neurons that respond just to eyes. If it sees eyes, it'll fire. If it sees a nose, another neuron will fire. Another one to the mouth. In the left half of the brain, there are neurons specialized for recognizing faces. And if we're communicating, talking to people, have friends or baby or family, it's important to be able to recognize their face. So this area of the brain has all these specialized neurons for recognizing complex objects, including faces. But the left half of the brain, think about language, temporal sequences, rhythmic patterns, portions, pieces, parts. Same thing with face. There are some neurons here and in the amygdala and in the hippocampus that recognize entire faces, but predominantly the left half will recognize parts of faces. There are neurons that recognize just parts of faces. However, and this goes into some of the differences, right and left half of the brain. The right half in the temporal area also has neurons that will respond to eyes, lips, noses, but it's the right temporal area which recognizes entire faces. Entire faces. So it will respond to an entire face. In fact, the right hemisphere is specialized for recognizing faces. It can learn faces. It can learn family members. It can learn movie stars. It can recognize the face of your pet. And a consequence, if a person had damage to the right temporal lobe, to this area here, they could lose the ability to recognize faces. They can go to the mirror and they wouldn't recognize their own face. Their husband or wife would come home and they wouldn't recognize them. They wouldn't recognize their own dog. If you're a farmer, have cows, a rancher, you wouldn't recognize the faces of your cows. And some ranchers, Bessie has a name and all the different cows. And this is called prosopagnosia. It's a very serious disorder that's often misrecognized. Agnosia, gnostic means to know. Agnostic, agnosic, like aphasia. The A in front means can't, so agnosia means you don't know. Prosopagnosia refers to an inability to recognize faces, and this can cause a lot of problems, including paranoia. I've gone home, and my wife is different. Look, you go home, your husband doesn't look the same, your wife doesn't look the same, your children don't look the same. Become paranoid. Somebody they've been replaced by imposters. And this is actual psychiatric disorder. It happens among older people. They go, oh, well, it's some psychological. No, it's actually destruction. If instead there was just partial damage, they might say, oh, there's Aunt Sally, and it's not Aunt Sally, it's a stranger. There's my boyfriend, well, it's not them. Start thinking faces are familiar when they're not. Okay? So, for ladies, next guy walks and goes, hey, haven't we met before? Well, maybe he's got some kind of damage in here that make him think he's seen you when he hasn't. Yes?
So, I know some people are really good with faces, like they say, oh, I can't remember names, but are really great at recognizing faces.
I'm like that, yes.
So what does that mean? Do they have like people are weak in that area? Do they have like, I don't know, something going on there? Or do people have like extra great areas right there?
Well, I know in my own case that I recognize faces. I mean, I can see somebody somewhere, and years later, I'll recognize that person, remember where I saw them. But if they can tell me their name 10 times, and I'll forget. My father and my grandfather, same problems. So there's some kind of genetic basis there.
Is that a problem? Like, is something...
Hey, it's a problem if you have a girlfriend, you can't remember her name after 3 days. I think like this. You can have people who have fantastic musical abilities, and actually it's because they have a large area of their brain devoted to that capacity. And they might have trouble with another area because there's only so much brain. And so certain functions can be highly developed, and others are crowded out because of more area. We go back to language. Females have more area of the brain devoted to language. We see that female infants, they start talking earlier than males. Their sentences become longer. They learn more words at a faster rate. They talk more quickly. They're more articulate. This is not some plot by male chauvinists, because what we see is cross-culture, is that females start developing language at an earlier age and more. But we see that females will dominate professions involving language. I mean, like secretaries, telephone operators, okay? And that's because females have a greater amount of the brain devoted to speech and language. In consequence, you have a male and a female. They both have massive strokes. The male is going to be more severely affected. He's not going to recover as quickly, and he's not going to recover language as much. And that's because the female has actually more area devoted to speech. And if you think about evolution or development, it's necessary, female, if you think about evolution, 10,000, 100,000 years of gathering groups, females going out gathering fruits and vegetables, chattering, they got the babies, males out hunting. You're not going to be talking because you're going to scare off the game. So males have to develop greater visual spatial capability. We're talking about 100,000 years of evolutionary pressure. Anyway, going back to, in answer to your question, yes, certain areas of the brain, there's sex differences, but there's also individual differences as well, because there's some males who can just, they just can't shut up. And there's some females who just don't really want to talk that much. So there's always individual variation.